Hello friends, today we'll be learning about the one of the practicals of digital communication subject which goes by the name of line codes. So what is line codes? Binary ones and zeros such as PCM signaling may be represented in various serial bit signaling formats called line codes. The simplest way to represent a 1 is by a square pulse and a 0 is by 0 volts. But the simplest may not always be good enough, as a long sequence of zeros may appear as a loss of transmission. In order to take care of this, line codes are used. There are various types of line codes which I'll be showing in the experiment. First, we'll have a look at the bit pattern which I'll be using. If we look at the MS Castronica kit, there are two patterns available. I'll be using pattern 2, so we'll have a look at pattern 2. We'll switch on the kit first, and there's a ground here. There's a pattern 2 available here on the kit. We'll be having a look at pattern 2 on the DSO. So this is pattern 2 which we observe on the DSO. I'll stop the pattern and then you can see that it is 10100 and it repeats after that. So we can check the bit time of this pattern. We can check it by using cursors. We put the cursors on the time menu and then we check. It shows the time to be 1 millisecond, the bit time to be 1 milliseconds, and the frequency to be 1 kilohertz. So we'll be applying pattern 2 to the code generator input. These are the various types of line codes available on the kit. We'll be checking Unipolar RZ. So we'll be checking the output on DSO. Before we go on DSO, I'll show you what the unipolar return to 0 line code looks like on paper. So as we have a bit pattern of 1 here, the unipolar return to 0 will go high for only half of the bit time. If this is TB, which is the bit time, the unipolar RZ pattern will be high only for half of the bit time. So a 1 will look like one will look like this, with this the width of the pulse being TB by 2. For 0 it remains 0, and for 1 again it will go high but only for half of the bit time. This is how a unipolar RZ looks on paper. Now we'll have a check on DSO. So now we'll have a look at unipolar RZ on the DSO. As you can see, this is the bit pattern 10100. Now this is the unipolar pattern. For 1 it is remaining 1 but only for half of the bit time, and for 0 it is remaining 0. If I overlap both the signals, you can see that for exactly half of the bit time every one is remaining high. This is how unipolar RZ's PSD looks like. We have a main lobe which goes from 0 to 2 times the normalized frequency, which is 1 kilohertz in our case. So for RZ signaling, the pulse duration is TB by 2 instead of TB as used in NRZ signaling. The demerit of unipolar RZ is that it requires 3 dB more signal power than polar signaling for the same probability error. Moreover, the spectrum is not negligible for frequencies near DC. We'll have a look of the PSD on DSO. We are having a look at the PSD of a unipolar signal. We can change the window to Hanning, and now we'll adjust the scale to have a better look. We shift the position so as to get the first null. We can check the null frequency by using cursors. We can move the cursor to the first null and we'll see that the frequency there is 2 kilohertz. Our bit rate was 1 kilohertz. So the first null occurs at twice the bit rate, so which is 2 kilohertz. For the same bit pattern, if we try to look at the polar RZ, the pattern will be for polar RZ we get for 1, the pattern will be high for half of the bit time, but for 0 also it will go negative for half of the bit time. Then it will return to 0 for the rest of the pattern. So when we have the bit high 1, that is 1, we'll get a polar RZ looking like. The duration of this bit is TB by 2. If the duration of the main bit is TB, then the duration of this is TB by 2. Similarly, if we go for the bit to be 0, the pattern will be looking like. And this continues. Next we have a 1, so therefore it will look like. Similarly, for the next two zeros, it will be negative for only half of the bit period. So this is how a polar RZ waveform pattern looks like. Now we'll check the same pattern on the DSO. This is the waveform of a polar RZ signal. This is our bit pattern again, and now this is the polar RZ signal. If I move it, if I overlap both the signals, we can see that for half of the bit rate, for a 1 it remains high, and for a 0, for half of the bit rate it remains 0. This is how the polar RZ PSD looks like. The demerits of bipolar signaling are that the receiver has to distinguish between 3 levels, plus A, minus A and 0, instead of just 2 levels in other signaling formats. The merit of this type of signaling is that it has signal error detection capabilities built in. Any violations can be easily detected. We'll have a look at the PSD on DSO. This is the PSD of a polar RZ signal. We'll change the window again to Hanning, and we'll adjust the scale accordingly. We'll measure the null frequency with the help of cursors. Again, as you can see, at twice the bit rate, we get a first null. This is how the PSD of a polar RZ signal looks like. So in case of bipolar NRZ, the pattern looks like when we have a bit pattern high, for the first time the bipolar NRZ goes to a high and it stays there till the bit is completed. So this is how the first one would look like. For 0, it remains 0, but for the next one, it will go to a lower level. This keeps on alternating. So, so the next one will be again high, and the next high will be again low. So this is how the ones keep on alternating. For the second one, the bipolar NRZ pattern will go low, and it will stay low till the bit pattern is high. And it will remain 0 for the next two zeros. This is how a bipolar NRZ looks on paper. Now we'll have a look on DSO. This is the bipolar NRZ signal. As we can see, if I overlap both the signals, every alternate one will show a high to low condition. This continues as the bit repeats. So this is the PSD of a bipolar NRZ signal. As you can see, the main lobe ends at 1 and the second lobe NZ2, and this keeps on diminishing as we go ahead. The demerit of polar NRZ is that it has a large PSD near DC. The merit of this coding is that it is easy to generate, although positive and negative power supplies are required. This is the PSD of a bipolar NRZ signal. We'll change the window to Hanning and we'll adjust the scale to have a better look. We'll measure the first null with the help of cursors. As we can see, the first null is being observed at 1 kHz, and according to the graph I have shown you, the first null will occur at 1 times the bit rate, which is 1 kHz. In case of Manchester signal, if the bit pattern is high, then the Manchester signal shows a high bit for half of the bit time and a low bit for a half of the bit time. So a 1 will be represented in Manchester signal as, while in case of a 0, it will be low for half of the bit time and it will be high for the other half. So this is how a 0 is represented. Similarly, the 1 is represented again with a high and a low. The next two zeros are represented in the same way as the initial 0 was represented. Now we'll have a look at the Manchester signal on a DSO. Now we move on to Manchester or split phase signaling. It is also called as alternate mark inversion. If I overlap both the signals, we can see for a bit to be high, it first remains high for half the bit rate and then goes down to 0 for the next half. Similarly, for a 0, it remains 0 for the half of the bit rate and then goes high for the next half. This is how a Manchester signal looks like. This is the PSD of a Manchester signal. As you can see, the main lobe is starting from 0 to 2. The null bandwidth of a Manchester format is twice as that of the bipolar bandwidth. However, the Manchester code has 0 DC level on a bit by bit basis. Moreover, a string of zeros will not cause a loss of the clocking signal. Now we'll have a look at the Manchester PSD on the DSO. This is the PSD of a Manchester signal. We'll change the window to Hanning and we'll adjust the scale. We'll measure the first null with the help of cursors. As we can see, the first null occurs at twice the bit rate, which is around 2 kHz. This is how the PSD of a Manchester or split phase signal looks like. Thank you and thanks for watching.